Hello and welcome. Today, we're diving deep, literally, into the Earth's heat. Most people know about geothermal energy, tapping into natural hotspots where heat, water, and permeable rock align perfectly. But these spots are rare. What if we could access the immense heat energy found almost anywhere deep underground? That's the promise of Enhanced Geothermal Systems, or EGS. Unlike traditional geothermal, EGS doesn't wait for perfect natural conditions. It aims to create them. It's about engineering a geothermal reservoir where none exists, unlocking heat deep within the Earth's crust, even miles down. So, how does it work? First, geologists identify locations with very hot rock, often granite, buried deep beneath insulating layers. Then, advanced drilling techniques borrowed and improved from the oil and gas industry push wells down several kilometers to reach temperatures potentially over 400 degrees Celsius. Now comes the enhanced part, reservoir stimulation. Water is injected under high pressure into one well. This doesn't usually create big fractures like fracking, but rather nudges open tiny pre-existing fractures in the rock, a process called hydroshearing. This creates pathways, making the hot, dry rock permeable. Once this network is established, water is circulated down an injection well, flows through the hot, newly permeable rock, absorbs the heat, and comes back up through production wells. At the surface, this intense heat generates electricity, either directly using steam or indirectly via a binary cycle system, where the geothermal fluid heats a secondary liquid that drives a turbine. The cooled water is then sent back down, creating a continuous loop. Reaching and managing these deep hot zones requires serious technology. Drilling through hard, hot rock miles deep is tough. Innovations like directional drilling allow more contact with the hot rock from a single pad, while better drill bits and pressure management systems have drastically cut drilling time from months to weeks, making it more economical. Precisely managing the stimulation phase is critical to increase permeability without causing issues like noticeable earthquakes. This involves careful pressure control and sophisticated monitoring using high-temperature sensors. Some newer concepts, called closed-loop systems, even circulate fluids entirely within sealed pipes deep underground, potentially reducing water use and the need for stimulation altogether. And of course, we need materials, casings, sensors, electronics that can survive these extreme high-temperature, high-pressure environments for decades. EGS isn't without hurdles. The upfront costs for deep drilling and reservoir creation are significant, though innovations are rapidly bringing them down. The U.S. Department of Energy even has a goal to cut EGS costs by 90% by 2035. Induced seismicity, small tremors caused by fluid injection, is a risk that needs careful management through site selection and controlled operations. Ensuring the engineered reservoir stays permeable and productive for 20 to 30 years is also a technical challenge. Despite the challenges, the potential is enormous. EGS could provide clean, reliable, baseload power 24/7 anywhere in the world, complementing solar and wind power perfectly. It's a steady energy source that doesn't depend on the weather. Plus, the hot water brought up can be a source for valuable minerals like lithium. With ongoing research, falling costs, and successful projects moving towards commercial scale, enhanced geothermal systems are poised to tap into the vast, clean energy resource right beneath our feet, playing a major role in our future energy mix. Thanks for tuning in.